Picture this. You wake up one morning and you feel a little bit sick. No particular symptoms, just not 100%. And so you go to the doctor, and she also doesn't know what's going on with you, so she suggests they run a battery of tests. Turns out you tested positive for a very rare disease that affects about 0.1% of the population, and it's a nasty disease, horrible consequences, you don't want it. So you ask the doctor, how certain is it that I have this disease? And she says, well, the test will correctly identify 99% of people that have the disease and only incorrectly identify 1% of people who don't have the disease. So that sounds pretty bad. I mean, what are the chances that you actually have this disease? I think most people would say 99% because that's the accuracy of the test. But that is not actually correct. You need Bayes' theorem to get some perspective.
Bayes' theorem can give you the probability that some hypothesis, say that you actually have the disease, is true given an event, that you tested positive for the disease. To calculate this, you need to take the prior probability the hypothesis was true, that is, how likely you thought it was that you had this disease before you got the test results, and multiply it by the probability of the event given the hypothesis is true. That is, the probability that you would test positive if you had the disease. And then divide that by the total probability of the event occurring, that is, testing positive. This term is a combination of your probability of having the disease and correctly testing positive, plus your probability of not having the disease and being falsely identified. The prior probability that a hypothesis is true is often the hardest part of this equation to figure out, and sometimes it's no better than a guess. But in this case, a reasonable starting point is the frequency of the disease in the population, so 0.1%. And if you plug in the rest of the numbers, you find that you have a 9% chance of actually having the disease after testing positive.
Which is incredibly low if you think about it. Now, this isn't some sort of crazy magic. It's actually common sense applied to mathematics. Just think about a sample size of 1,000 people. Now, one person out of that 1,000 is likely to actually have the disease, and the test would likely identify them correctly as having the disease. But out of the 999 other people, 1% or 10 people would falsely be identified as having the disease. So if you're one of those people who has a positive test result, and everyone's just selected at random, well, you're actually part of a group of 11 where only one person has the disease. So your chances of actually having it are 1 in 11. 9%. When Bayes first came up with this theorem, he didn't actually think it was revolutionary. He didn't even think it was worthy of publication. He didn't submit it to the Royal Society, of which he was a member. And in fact, it was discovered in his papers after he died, and he had abandoned it for more than a decade. What would happen if you went to another doctor, get a second opinion, and get that test run again, but let's say by a different lab, just to be sure that those tests are independent? And let's say that test also comes back as positive. Now, what is the probability that you actually have the disease? Well, you can use Bayes' formula again, except this time, for your prior probability that you have the disease, you have to put in the posterior probability, the probability that we worked out before, which is 9%, because you've already had one positive test. And if you crunch those numbers, the new probability based on 2 positive tests is 91%. There's a 91% chance that you actually have the disease, which kind of makes sense. 2 positive results by different labs are unlikely to just be chance. But you'll notice that probability is still not as high as the accuracy, the reported accuracy of the test. Bayes' theorem has found a number of practical applications, including notably filtering your spam. Traditional spam filters actually do a kind of bad job. There's too many false positives. Too much of your email ends up in spam. But using a Bayesian filter, you can look at the various words that appear in emails and use Bayes' theorem to give a probability that the email is spam, given that those words appear. Now, Bayes' theorem tells us how to update our beliefs in light of new evidence, but it can't tell us how to set our prior beliefs. And so it's possible for some people to hold that certain things are true with 100% certainty, and other people to hold those same things are true with 0% certainty. What Bayes' theorem shows us is that in those cases, there is absolutely no evidence, nothing anyone could do to change their minds. And so as Nate Silver points out in his book, The Signal and the Noise, we should probably not have debates between people with 100% prior certainty and 0% prior certainty because, well, really, they'll never convince each other of anything.